Okay, so today we're starting chapter 2, and chapter 2 is all about geodesic congruences. And what I mean by a congruence is basically just a whole family of curves that don't intersect. And at first, I'll be talking about time-like curves, time-like geodesics more specifically, and then at some point we'll go into the null case, which is full of subtleties and interesting features. But for the time being, it's going to be time-like curves, time-like geodesics. And again, the whole idea is that a congruence is a family of non-intersecting curves. And if we're talking about geodesics specifically, we could be talking about curves that are, that are not geodesics, but, for our purposes here, we're going to be talking about geodesics. So we're talking about a family of non-intersecting geodesics. If we do have points of intersection, then we have a singularity of the congruence, and that's something we'll talk about. But those are exceptional cases that, we'll basically rule out as part of the definition here. So here's one of the time-like geodesics. Here's another one. Here's another one. Here's a fourth one. And what you have to imagine here is that I'm really filling three-dimensional space. I'm filling it up with curves, and we have curves basically everywhere. So at every spatial point, we have a curve that passes through that point, and only one curve that passes through that point, because that's the non-intersecting condition. So we have a whole family of curves like this, and what we're going to be trying to do here is to describe the behavior of these curves in reference to one of them. So we're going to pick one of them. We're going to call it a reference geodesic, and then what I want to do is to describe the behavior of neighboring geodesics using our deviation vector that we talked about last week as the main tool to do that. You had a question?
Well, at each point in three-dimensional space, you can have light passing to that point in any direction. So, don't you mean in one dimension if they don't intersect?
Sorry, I didn't quite get that.
You're saying geodesics don't intersect.
Yeah.
But that's only if you're working on a plane.
No, I'm thinking about this in three-dimensional space. So I pick a point in three-dimensional space. And it's true that any one geodesic can go in any direction through that point. But the point is that there's only one geodesic passing through that point in my family. So I'm talking about the whole family.
You pick a congruence. There are geodesics which pass each other, obviously, but you pick like a flow such that
I pick a family. And for that family, of course, I can have other geodesics passing through those points, but they're not part of my family. So the family only has those geodesics non-intersecting. So we're going to have one, geodesic that's going to be a reference, and then a reference geodesic, and then we're going to have a bunch of neighboring geodesics. And we're going to be working locally. And what I want to do is to describe the behavior of the neighboring geodesics through the behavior of the deviation vector that we introduced last time, and will be basically the essential ingredient in our description. So I'll come back to that. What we're going to be basically deriving here are evolution equations for the deviation vector, and we're going to see what they tell us. What I want to do first, though, just to introduce the scene a bit, is to do something like that, but in a more familiar, maybe, setting. And we're going to go back to 3D Newtonian physics, and we're going to be doing this just to introduce the scene again in the context of fluid mechanics. So let me explain why I want to do this, and then we'll pursue this for a little while and see where that leads us. So let me just say that this is to be continued. And I'm going to take a tangential path here and do something a little bit different. So let's talk about 3D Newtonian fluid mechanics. So here's the thing. So I'm still going to have, I'm going to display a space-time diagram here, just for illustrating what I want to, introducing what I want to talk about. So let me consider a time, t1, say, and let's consider a fluid configuration at that time. So here's where it is. So this is just, some fluid configuration at that time. Now, what you do in fluid dynamics is to say that in your fluid, your fluid is just decomposed into a whole bunch of fluid elements, and you associate, a fluid element with a point in space. So each point in space basically has a fluid element around it, and that fluid element, is one of those things that's supposed to be very small on macroscopic scales, but very large on microscopic scales, so that you can still have a whole bunch of molecules inside each fluid element. And each fluid element will have, its own density, its pressure. It will go in some direction with some velocity. So all of those things are, basic ingredients of fluid mechanics. So over here, for example, we have one fluid element. And over there, we have another fluid element. So this is a fluid element. And what you do in fluid mechanics is, as the system evolves, as the fluid configuration evolves in time, you track the motion of each fluid element. So you can imagine, for example, that you take all the molecules in here and you paint them red, and you follow all the red molecules as the system evolves in time. And those ones over here are going to be painted blue, and you follow the blue molecules as the system evolves in time. And the collection of blue molecules is going to be the fluid element at all times. The collection of red molecules is going to be the fluid element, at all times. So at a later time up here, the fluid configuration will have changed. Pressure will be, acting. External forces might be acting. I really don't care what's going on here. What I care about is that I can track this fluid element in time, and I will know that at a later time it's going to be up here, and this one is going to be up here somewhere. And thinking about this, what we're saying is that, well, each fluid element will trace a word line in, 3+1 space-time. So we have a word line passing through here that tracks the motion of the red molecules, and we have another word line through here that tracks the motion of that fluid element. So those word lines that that basically tell us about the behavior of fluid elements is an example of a congruence. So what I'll do for the next little while is that I'll think in terms of fluid dynamics, but eventually I'll just abstract away the fluid, but we're going to keep the curves. And we're going to be thinking about the behavior of the curves, but the intuition we're going to have by playing around with the fluid stuff, I think will be useful. So you see where I'm going, so the connection between the two things. Yep.
So just one clarification. These fluid configurations cannot tear apart in the middle of a certain length also.
That would be a singularity of the fluid dynamics, so I'm going to rule this out. So it would be a case where you might generate holes or things like that, or So I'm just assuming that this doesn't happen. Right. So basically, we have a bunch of curves like this that track the motion of fluid elements. And I could call this one the reference element. And I could look at this one and say that it's a neighboring fluid element. And there's going to be a displacement vector between the two that I'm going to call xi. And this will be xi as a function of time, because as the fluid configuration changes, the distance between this fluid element and the reference fluid element changes. So xi as a function of time is the displacement between a given fluid element and the reference fluid element. And of course, if I say that this is, position x1, and if I say that this is position x naught, well, c is just going to be, in three-dimensional space, the difference between the two positions. So that's something I can do in Newtonian physics that simplifies the discussion. That's something, of course, that I would never do in curved space-time because we don't have this notion of a vector that points from point to point. Okay. So here's the so that was the definition of the displacement vector in this case of fluid dynamics. A question that I could be asking then is, well, what is going to be the relative velocity between the fluid elements? So the relative velocity between those two fluid elements, well, clearly it's going to be the time derivative of that displacement vector. And it's going to be the velocity field of the fluid evaluated at x1 minus the velocity field of the fluid evaluated at x naught. So by velocity field, I mean that if I pick a fluid element and I track it, I know it's going to be moving with some speed in some direction. So if I pick this one, it's going to be moving, with some speed in some direction. This one is also going to be with some, moving with some speed in some direction. So for each fluid element, I have a vector, a velocity vector, and therefore I have a velocity vector that varies with spatial position, also with time. I didn't indicate the time dependence. And that's what I mean by a velocity field for each point within the fluid. I look at what the fluid element is doing, and that's how I define my velocity at that point. So in the space-time thing, we're going to have something analogous to that we're going to be tracking also when we look at the relative behavior of two neighboring geodesics. So if I'm talking about large displacements, of course, I have to leave it at that. If I'm talking about small displacements, what I can do is to do a Taylor expansion about x naught. And because x naught is my reference point, and because I'm talking about neighboring geodesics, I'm going to do a Taylor expansion and keep things to leading order. So in components, I can say that the j component of the relative velocity is just going to be, well, the v component of the velocity, the j component of the velocity field evaluated at x naught plus c minus the velocity field at x naught. And I can do the Taylor expansion, and from this guy, I get Vj, comma k, ck, plus higher order terms in c that I'm going to ignore. So we're going to be talking about small displacements, and what I have here is an equation that tells us that the rate of change of the vector c is to leading order proportional to c itself times something in front, which is the gradient of the velocity field evaluated at x naught. Okay? So that's really the starting point of the whole discussion, and we're going to see where that leads us and what the counterpart will be to that in the congruence discussion. So let me just rewrite this. I'm going to say that dc dt is going to be some matrix bjk multiplying c, and I forget higher order terms, and bjk is the gradient of the velocity field evaluated on the reference fluid element at that time. It depends on time, but it's always evaluated at a fixed position. So I should indicate the time dependence here and the time dependence here. So evaluated at the reference fluid element. So no mystery so far? Okay, so the whole point is that I want to investigate the nature of that matrix. So Bjk is going to be some 3x3 matrix. And in general, I cannot expect that this matrix will have any symmetries. So a tool that's always used in those situations is that you just break it down into its smallest pieces. A fancier way of saying this is that you just break down the matrix into its irreducible pieces, and you look at each piece separately, and then when you know what each piece is doing, you put it all together. So we're going to decompose. So this is a matrix without symmetries. So we're going to decompose it into irreducible pieces. And that's something we're going to do also in the space-time version of this. So what do I mean by that? Let me just write it down. I'm going to break down, that's a theta. I'm going to break it down into something that's purely diagonal, and I'm going to call this the trace part. I'm going to break it down into something else that I'm going to call the trace-free part, the symmetric trace-free part. And I'm going to break it down into an antisymmetric part, omega jk. So this is going to be the trace part. This is going to be the symmetric trace-free part. And this will be the antisymmetric part. So if you're given a matrix, first of all, you can always decompose it into symmetric and antisymmetric pieces. That's always something you can do. So we've done that here. But in addition to that, I've taken the symmetric part and I've broken it down further into something which is pure trace, the first term, and something which is, symmetric but without the trace term, therefore symmetric trace-free.
Is omega also trace-free?
Yeah, because it's antisymmetric. Right?
Right.
Yeah. So definitions for these things. Well, theta is just, as I said, the trace of that matrix. And this follows because when you take the trace of this, you get the trace of the unit matrix, which is 3. The 1/3 is there to make up for that. So you get theta from that. You get nothing from here because, by definition, that's trace-free. And you get nothing from here because, as we just said, an antisymmetric matrix will always be trace-free. So theta is defined by this relation right here. Sigma jk is going to be the symmetric part of B minus the trace part. And finally, the omega matrix is just going to be the antisymmetric part of the B matrix. So basically, that's how you define these things. And when you put it back together, you get the full B. Okay, so just to make sure that all of that is very concrete, if I write it in matrix form, well, we know what this stands for. It's going to be 1/3 omega, 1/3 theta here, 1/3 theta here, 1/3 theta here, and we get 0 everywhere else, right? Sigma ij is going to be another matrix, and the first requirement is that it has to be symmetric. So we're going to have a sigma 1,1 up here, sigma 1,2 up here, sigma 1,3 up here, but this one, of course, has to be equal to this one, right? So sigma 2,1 has to be equal to sigma 1,2. Here, sigma 2,2 is not constrained, and sigma 2,3 also is not constrained. This guy over here, sigma 3, 1, has to be equal to sigma 1, 3. This guy has to be equal to sigma 2, 3. And the one that's left over here has to be such that the trace vanishes, so it has to be minus the sum of sigma 1, 1 and sigma 2, 2. And finally, omega jk has to be an antisymmetric matrix, so there's no entry here. There's going to be an omega 1, 2 over here, an omega 1, 3 over there. Here, we're going to have minus omega 1, 2, 0, omega 2, 3, minus omega 1, 3, minus omega 2, 3, and 0. So if you count the components, we have one component up here. We have 1, 2, 3, 4, 5 here. It would be 6 for a symmetric matrix, but we remove the trace, so we get one less. And here we have 1, 2, 3 components, because it's an antisymmetric matrix. And if we add this up, we get 9. And that, obviously, is the total number of components we had in the original B, 3 by 3, equals 9 usually. So that's just a way of breaking down a matrix into its smallest possible pieces. And the next question is, well, thinking still about the fluid, what is each piece going to do on the fluid? Let's think about what each piece is doing, and then we can put it all back together, and that's going to be the action of the full B, right? So no questions so far? Okay, good. So this decomposition is something we'll encounter also in the space-time discussion. Okay. Let's think about the expansion. And of course, I've chosen the words. I didn't call them here. So this is called the expansion. Theta is called the expansion. This guy is called the shear tensor. And this guy is called the rotation tensor. And the names, obviously, are very suggestive. So I just want to bring this out. Okay, theta is the trace of B, which is the velocity gradient, which means that in traditional notation, it's just the divergence of the vector field attached to the fluid. And that, if you've done fluid mechanics before, you'll recognize as the rate of expansion of fluid elements as they move around the fluid. But that's what I want to, I just want to spend a little bit of time, describing this. So the claim is that this is the rate of expansion of the volume of fluid elements. And I should say fractional rate of expansion. Okay. So one property of my fluid elements is that as I keep tracking the molecules like this and keep the fluid elements under scrutiny, well, first of all, so the fluid element always captures the same number of molecules. So we have number conservation, but I don't care about that. I mean, it's true, but I don't care about it. As I keep tracking the molecules, the mass contained in a given fluid element is conserved, and that I care about. So I'm going to use conservation of mass here as a way of explaining where the expansion comes from. What is not conserved is the volume of each fluid element. So as I keep tracking the molecules, well, depending on what the fluid is doing, the size of the fluid element will change in time. It may expand, it may contract, as I keep tracking the same number of molecules. The shape also will change, and we'll talk about shape changes when we talk about the shear. But right now, I want to keep track of how much volume is contained in a fluid element. Of course, we're talking about infinitesimal volumes in this case. So I'm going to introduce mass conservation as the way to address this. And mass conservation is expressed by the continuity equation, right? So we have a mass density, which is the amount of mass contained in a fluid element divided by its volume. And we also have a mass current, which is going to be rho multiplying by the velocity vector. So that's the current density associated with the mass. And the continuity equation is, well, contained in the statement that the partial rate of change of rho with respect to time is going to be the divergence of the current density. And that's the equation I have here. So you've all seen that a long time ago, mostly in the context of E&M. In E&M, that would describe charge conservation. Here, we're talking about mass conservation. So my density here is the density of mass. OK, so let me just write this out in a slightly different form. So what I'm going to do is to expand this. I'm going to just propagate the differential operator here. So first, I'm going to get rho that multiplies the divergence of V. And then I'm going to get V that multiplies the gradient of rho. And what I'm going to do is to lump those two things together. And throw the other one over to the left, to the right-hand side. That's the thing I want to have a look at, because that's the thing that's related to my expansion parameter, right? My expansion quantity. Do you recognize the left-hand side? I'll take that as a no. This is the total time derivative of the density as I follow the motion of the fluid element. Let me just explain that. As we follow a given fluid element, and we ask, so for example, so at t equals, at t equals, so let's focus on this fluid element over here. I'm going to be asking what is the density at t, and what is the density at a later time, t plus delta t. The density at t is obviously going to be the density of the fluid at the position of my fluid element. At t plus dt, the density of the same fluid element is going to be what the density will be at the later time, obviously, but I have to account for the motion of the fluid element in space, right? Because the fluid element is going to be displaced relative to its previous position. So what I have to do is to evaluate the density at the right spot, which is the new spot of that fluid element. The total change, d rho, is going to be the difference between those two things. And that is something I can evaluate as a Taylor expansion. So I get the partial derivative with respect to t multiplying dt. And then I get dx multiplying the gradient of the velocity, of the density. And then, of course, there would be higher order terms that I don't care about when I take the limit. And therefore, if I differentiate with, if I divide with respect to dt, I get dx divided by dt, which is clearly the, the velocity of the fluid element, multiplying delta rho. So that combination is the total time derivative of my density if I follow the motion of the fluid element. If I don't follow the motion of the fluid element and I just ask what is the time derivative of the density always here at this particular spot in space, then I get that. I get the partial derivative of rho with respect to t. But if I say that I'm going to be tracking the motion of the fluid element as it moves from here to there while I take the time derivative, then I have to include this term as well. So usually this is something that always occurs in fluid dynamics, and it's sometimes called the convective derivative of the density. For us, it's something we should recognize because, in a non-relativistic setting, this is an approximation for rho differentiated in the direction of the forward velocity of the fluid element. Because in a non-relativistic setting, the forward velocity would be approximately would be approximately equal to 1 in the time direction and equal to the spatial velocity in the spatial components. So this derivative is basically tracking the changes as you follow the motion of the fluid element, or more generally, as you follow the word line of some, the word line of something, right? So this is something we expect. This is something we've seen a lot, or that we'll see a lot in GR, that we recognize as coming from, say, a GR context, but it's really something that more fundamentally just describes a time derivative that keeps track of the motion of our fluid element. All right? Okay. Okay, so now we're back here, and we see what's going on. We have the result that that quantity over here, which I was interested in, is minus 1 over rho d rho dt. So the divergence of the velocity field has to do with a change in the density as we keep track of the fluid element. And the density can only change if the mass can't change within a fluid element. The density can only change if we have a change in volume. So the next step and the last step here is just to rewrite this in terms of the delta V that I introduced before. And obviously, if I differentiate delta V, if I differentiate rho and dm is constant, then I produce a minus sign, I produce a dv over, a 1 over dv over 2, and I produce a rate of change of dv. So when you put it all together, you get rid of this minus sign, you get 1 over dv, and then what you're constructing here is the rate of change of the volume divided by volume. So it's the fractional rate of change of the volume of a fluid element. So if you have a diverging, so a fluid that diverges, so that the velocity field has a non-zero, a positive divergence. So if it's all going in directions like this, that each fluid element is diverging away from each other, well, that means that the fluid is expanding in space, and if you keep the mass constant, that means the volume is expanding, and that's what we find here, that for a positive divergence, we get a positive rate of increase of each volume for each fluid element. If the divergence is negative, that means that the fluid is converging on itself, right? The velocity field is directed inward, and that means that the fluid is, contracting in space, and that means that each fluid element in that case would be contracting as well, and this would be negative when this is negative. So bottom line is that our expansion parameter is the fractional rate of change of volume. So the whole scaling of the fluid is described, by this expansion parameter. Any questions about that? Yep.
But this is only true for fluid which has no pressure.
No. Pressure has nothing to do with this. Pressure will tell us how the fluid elements move, right? So a pressure gradient across a fluid element will tell us that there's an acceleration on each fluid element.
But it adds a term to the continuity equation.
No. Mass conservation is, strictly given by the continuity equation. Other questions? Okay, let me talk about the shear. And to talk about the shear, what I'm going to do is to pretend that this is 0 over here. We know what this is now. We know what it does. I'm going to pretend that this is 0. So I'm just going to rewrite this equation, pretending that the only thing that's acting is the shear tensor. So I'm going to set theta equals 0, and I'm going to set the rotation tensor to be equal to 0. And now the evolution equation for my deviation vector is just going to be given by the shear tensor. The shear tensor, we understand, is, did I lose my listing of components? Is a symmetric trace-free tensor. Now, I have 5 independent components for sigma, and I have a whole bunch of equations, so that's a little bit more complicated than it needs to be. So just to simplify the discussion, I'm going to assume that there's only one, that most of those guys here are 0, and that there's only one surviving component. And we're going to look at that, and we're going to see what's going on. So let's take sigma 1, 2. And from now on, I'll just call it sigma to be the only non-vanishing component. Just for the sake of this discussion. So I can do that. I can pretend that all the other ones are 0, and I still have a symmetric trace-free tensor, but now instead of having 5 individual components, I've boiled it down to just 1. And clearly, we can repeat this discussion for each one separately, and it's going to be the same story all over again, so we'll just do it once. Okay, so now if I write this in full, so sigma 1, 2 will couple only the x and y components of my deviation vector. So boiled down, I have that the rate of change of Cx is going to be sigma times Cy, and the rate of change of Cy is going to be plus sigma Cx. So let's try to see what this gives us. So I'm going to be plotting Cx and Cy. And just to see what this gives us, let's assume that we have a collection of fluid elements that forms a nice circle in that plane. So the reference fluid element is still at the center, and now I'm considering a whole bunch of neighboring fluid elements that at some time are, giving us the form of a circle. So we have, fluid elements in the shape of a circle, and that's going to be the initial shape at the initial time. And I want to see what the shape is going to shape into as we let the shear act. So what's going to happen at a later time? Okay. Well, basically, all I have to ask is what is going to be the displacement, the change in the deviation vector that's described by this. So per unit time. So for example, if I take a fluid element over here, then sigma y is 0, so that there's no displacement along x. But sigma x is equal to this unit, and that means that there's going to be a displacement along y, right? So this fluid element over here is going to be pushed upward a little bit, like that. That's the, that's the action. That's the, that's the meaning of those differential equations. They tell us what's going to happen in the next moment. If I take a fluid element up here, then these guys are going to be equal, and we're going to generate equal displacements in both x and y. So in that case, the displacement is going to be this way. If we're up here, then there's no displacement along y, but there's going to be a displacement along x. It's going to be pushing this way. So we just keep going like this, and I think you'll see where this is going. So if we're over here, then the displacement in y is positive, but the displacement in x is negative. So we get something positive from here, something negative from here. So now we get a displacement that goes this way. And we keep going like this. If we're here, if we're over here, it gets pushed down. If it's over here, it gets pushed in that direction. And if it's over here, if we're down here, it's going to be negative in both directions. So we're really going this way. If it's down here, then so this guy is 0, no displacement along y, but we get a negative displacement along x, so we go this way. And the last one over here is going this way. So as we, just give me a sec, yeah, what? Might as well.
Top arrow should be pointing right.
Oh yeah, that's in the wrong direction. Right, so this one over here, we get 0 for x, we get 1 for y, so we get a displacement along x, which is positive, so it goes this way. Very good. So what shape is this giving us? Well, we just joined the points, right? So it gives us something like this. And, well, it's not pretty, but it basically describes an ellipse. So the effect of the shear tensor, and here we've picked one component of that, is to take a circular shape in the fluid, and as time evolves, it will shear it. It will squeeze one direction, stretch the other direction in the shape of an ellipse. And we've played this game in one dimension, or I mean, we've played this game with one parameter. But if you played this game with all the other parameters in turn, you would get ellipses in various orientations. And if you put it all together, you would find that you get some ellipse in some direction, but you will always distort a sphere into something that's elongated, like an ellipse that's going to be squeezed in one direction and elongated in the other direction. That's the effect of the shear tensor. It just deforms the neighboring fluid configuration into something which is squeezed and elongated with respect to the initial shape. And an important property of this is that, well, you can actually prove from the relations here that the distortion does not affect the volume. So as you squeeze the circle into an ellipse, you can show that the volume, or here the area, inside the shape is going to be preserved. So there's a deformation of shape without a change in volume. So in the book, I go through that in a slightly different context. So you can read about that. You can also play around with different parameters, see how they would affect things. But all that changes basically is that you change the orientation, you change the axes. But what you always get is a given shape that gets distorted. And if you start with the circle, you get an ellipse, and that's the role of the shear tensor. It basically takes a spherical fluid element. Well, a collection of fluid elements around the neighboring fluid elements, so you take a shape around your reference fluid element, and that shape gets distorted as the fluid evolves in time. Okay. Any mysteries about any of this? Okay, so that's the shear, and we can do something very similar for the rotation. The rotation, so here again, I'm going to kill off a whole bunch of components just to simplify things. So first of all, we're going to set the expansion equal to 0, and we're going to say now that the shear is equal to 0. So we're going to focus on the rotation. And also, I'm going to take omega 1, 2 again to be, and I'm going to call it omega, is the only non-vanishing component. Which means that my equations now for dx cdt are going to be almost the same as what I had before for the shear, but now there's going to be a crucial minus sign in the second equation. So let's do the same thing. Let's consider a whole bunch of fluid elements around our reference fluid element, and let's give them initially the shape of a circle in that plane. And let's play the same game. If we're here, then this displacement is 0. This guy is, this guy is 0. This guy is non-zero. It's equal to the unit. And I get a displacement in the negative direction along y. So in this case, I'm pushed this way. If I'm over here, I get a positive displacement here and a negative displacement here. So I get something that's pushed, it's positive here, it's negative here. So, so I go this way. This guy, so this guy now is 0, so my displacement is along x. Something's not right. So this guy is okay. This guy. Oh no, sorry. What am I talking about? It goes this way. All right. This guy. Okay. So now it's negative in x and positive in y. So this guy is positive. This guy is positive also. So we go this way. So you see how it goes, right? It's always going tangent along the circle. So you can take my word for it that the displacements are always tangent. And basically all you're doing, whoa. Sorry about all this confusion. That would be very wrong. Tangent in the same direction. So what have I done? Yeah, okay. So basically all you're doing is to take the circle and you just rotate it on itself, right? That's what the equations mean. So here you take that spherical shape, and then you see that in time it continues to be a spherical shape, but now you see that there's an overall rotation that gets built up, and then as you keep following that in time, it will continue to build up, and omega then describes the rate of rotation. It's really the angular velocity associated with that rotation. So this is just a rotation of the original shape without distortion. And then if you play around again with different of those parameters with alternative parameters, then you'll find that you also have rotations, but they would be rotations in different directions. And the most common thing when you combine all three all three rotation parameters is the fact that, well, you can just, you can take a spherical ball and you can rotate it in arbitrary directions. And, but in all cases, you'll find that you get a rotation in some direction by some angle without introducing a distortion of the shape. So now that we have all that, well, we can go back to this decomposition over here, and we can put it all together, and we know what B is going to be doing. B is going to be basically a combination of all those elementary transformations that we talked about. In general, there will be an expansion, either positive or negative, so there will be a scaling of the fluid that, that's described by the trace term over here. There's going to be a distortion in the shape of neighboring fluid elements relative to the reference fluid element. So that's described by the shear tensor. And in addition to that, the whole thing is going to be rotating. So in general, you have a rich behavior, but if you break it down into pieces like that, you can understand each piece and you know precisely what they mean. Yep?
The higher orders of seeing that expansion, does that give any extra information?
Yeah, so if you really wanted to extend this to higher order, then of course you would have more pieces. So you would have another B field that would have now 3 indices to it. You could also decompose that into reducible pieces, but now the transformations would be much more complicated. So here we're dealing with linear transformations, which are simple. If you want to keep extra terms, it would be much more involved in terms of description. You can find that being done in places like elasticity theory. If you read old books on elasticity theory, you'll find that they'll do that. They'll actually go to higher order, and it's a mess. It's a big mess. In GR, certainly we won't do that. We'll be happy to keep it at first order because, in fact, it will turn out to be exact at first order, so we don't need to worry about higher order terms. So that's an advantage of GR versus fluid mechanics or elasticity theory. Was there another? Yeah, another question.
So this rotation gives rise to twisting effect as well, right?
Yeah. By rotation, I really mean a twisting of the. So you can imagine that the word lines are just twisting on themselves like that. Yeah. Okay, so we're all good with that. So of course, the point of all this is that while this is a sort of more elementary setting where we can understand these things, I think, and rely on the fluid behavior that we have some intuition about. Now I'm going to go back to the GR case. I'm going to go back to the situation where we don't have a fluid. We may have a fluid, but we don't have to have a fluid. And what we have instead are just a bunch of curves. We have this congruence of curves. But none of this here really relied in a big way on the existence of the fluid. So mostly I was relying on the existence of a bunch of trajectories. So the curves were very essential to this discussion. The only place where I introduced the fluid is through this discussion right here of mass conservation that allowed me to relate the expansion to the gradient of the velocity field. But if you think about this a little bit more deeply, what you find is that, well, this was just basically incidental. So the appeal to mass conservation in this case was just for me to simplify the discussion and relate it to something you knew, namely the continuity equation. But this relationship between the gradient of the velocity field and the fractional rate of volume, rate of change of volume as you follow a bunch of curves is something that, in fact, is not, essentially tied to this discussion of mass conservation. It was just a convenient way to get there. But this is something you could derive differently without appealing to a conservation statement. So basically, the bottom line is that basically all of this is something that never really relied on the material properties of the fluid. I can take it out, I can take the fluid out, keep the curves, and that's the situation we have in GR, except for the fact that now we're going to do everything in space-time as opposed to three-dimensional space with time added. That's the only distinction. But we're going to find, in fact, that the correspondence between this and that is extremely close. And in fact, the interpretation for all the space-time quantities is going to follow exactly from this discussion. There really is no need for introducing qualifiers or making conceptual changes. It's really exactly the same story. Yep, you have a question?
Just wondering about the expansion in GR. So in GR, the volume, that would be like a spatial volume that the slices are
Yep.
congruous?
Yeah, I'll talk about that. Yeah.
Okay, so
Yeah.
like that's not the Lorentz invariant though, so is theta not Lorentz invariant as well?
It is Lorentz invariant. I'll try to explain that when we get there. You had a question?
Yeah, just out of curiosity, in a non-Newtonian fluid like cornstarch, would this be different? This discussion?
I haven't studied non-Newtonian fluids for quite a while. I think so. I don't think it's going to be very different. So certainly the non-Newtonian nature of the fluid will change its dynamics a lot. So the equivalent. So the Euler equation that would be the description of the dynamics of an ideal fluid is not going to be applicable to a non-Newtonian fluid. However, I think anything that has to do with mass conservation would still be there. Anything that has to do with this way of describing things in terms of relative behavior would still hold. So I do believe that there's nothing to be changed here when you go from perfect fluids to non-Newtonian fluids. You can add viscosity to that without changing anything. So I think that's the answer. I mean, I would have to go back and check whether there's any surprises in non-Newtonian fluids, but my belief is that everything carries over without change. Other questions? Okay, so let me go back now to the first board. So we're going to close our parenthesis here and just go back to what we were doing before. Clear all of that. Okay, so back to congruences. Okay, so back to this diagram. I'm just going to redraw it. So we have a bunch of geodesics. I'm just going to draw two of them for the time being. And, well, we know how this works, right? We've carried out this construction before. We can do the usual thing where, first of all, having this, this whole, sequence of geodesics, we know that we have a vector field U, which is going to be everywhere tangent to the congruence. So we have a tangent vector field. And when we were playing around with geodesic deviation, I started out with two curves, and then I postulated the existence of a whole bunch of curves in between. Now it's very similar to that, except that the family gives us, the curves in between, so I don't have to put them in artificially. They're just there, given by the family. So that's one slight change with respect to what we were doing before. So we have the tangent vector field. We can do the same game of introducing cross curves by looking at how these curves are described parametrically, the same way we did it with the geodesic deviation. So we have this notion of a deviation vector, which is again defined as tangent to those cross curves. Although here the cross curves are not going to play an explicit role, but it's implicitly given here. And I'm going to import a lot of the results we had last week when we were doing all of this for geodesic deviation. So we have U alpha, which is the tangent vector field. To the congruence. And here I'm going to assume that, so we're dealing, first of all, with time-like geodesics. I should have said that. I'm going to assume that I'm using proper time as a parameter on each geodesic. So we're going to have a vector field that satisfies the geodesic equation in the usual form. And I'm also assuming that our velocity field is normalized to the usual -1. So we have that. We have C, which is the deviation vector, which we can think of as basically describing a displacement from the reference geodesic down here to a neighboring geodesic, but in the usual geometrical way of inventing these things where you introduce the cross curves and you make sure that this field, this vector field, is defined as tangent to cross curves. So it's a deviation vector field, which is tangent to cross curves. And this vector field, according to all the work we did last week, will have two essential properties. One is that the Lie derivative of xi in the direction of u is going to be equal to the Lie derivative of u in the direction of xi. And that means that C alpha differentiated in the direction of u is going to be the same thing as u differentiated in the direction of xi. And the other property that we saw last week we could always impose is the statement that the deviation vector is always going to be orthogonal to the tangent vector field. So that's a freedom we had left over. We proved that this was always a constant as you follow the congruence, and we can set the constant equal to 0 by taking out the component of xi that might have been originally in the direction of u. We can take this out. We've done that, and we're going to assume that that this condition can be imposed. So basically, all of this is imported from the discussion we had last week about geodesic deviation. I'm just importing all of this and using that as the starting point for the discussion of our congruence here. I'm going to come back to that Lie derivative equation in a couple of minutes, but now I want to introduce a couple of useful tools. I want to introduce a decomposition of the metric into a time direction and a spatial direction. I'll just write it out. So I have a preferred vector field in space-time, which is the tangent vector field to the congruence, and that can be defined basically as, that can be used to define a preferred time direction in space-time. So at every point in the space-time where I have my vector field, I can pick the direction of that vector field to be a favored time direction. And I can basically put myself in a frame in which the vector field is oriented along a long time at that point. And I can call that the time direction, and I can be working in a local Lorentz frame at that point, aligned with that time direction. That way of thinking is basically incorporated in this equation, which tells us that the metric can always be written as something that points entirely along time. And the thing to do that is to form a tensor from something that has this time information in it. So basically the only tensor that I can form from the thing that has the time information, which is the velocity field, is, the velocity field multiplied by the velocity field. And then what's left over is something that I'm going to declare is orthogonal to U and will represent the purely spatial pieces of the metric. So we have this piece, we have this condition that tells us that H is a purely spatial thing. And basically what we have here is a decomposition of the metric into a time piece and a spatial piece. And if you want to know what H alpha really stands for, H alpha beta really stands for, well, it's just that. So given the metric, given the vector field, we can decompose the metric into something purely along the lines of the vector field, and then something left over, and what's left over is obviously the difference between this and that, and that's what we get on the second line. I'll try to explain a little bit better what's going on here so that you all see what the thinking is behind this decomposition. But let me just work out a couple of interesting properties about this H. Well, first of all, I declared, so at this stage I was declaring that H alpha beta has to be orthogonal to U. But since we know what it is, we might as well verify. So let's verify that if I multiply on the left with U, I get 0. If I multiply on the left with U, I can use this metric to lower the index on the vector field, so I get U beta. And here I get U alpha that multiplies U beta. And this is equal to -1, so sure enough, I get 0. If I multiply on the right, well, it's the same story, right? Because it's a symmetric tensor. So we get U alpha from over here. We get U alpha that multiplies U beta. That's equal to -1. That's, again, 0. So if I wanted to invent a metric that represents really the spatial displacement in my congruence, that would be a pretty good That would be a pretty good candidate. That would be a pretty good candidate, I should say again. Because that piece of the metric is completely orthogonal to what I've declared to be the time direction, which is the direction of the vector field U. So that's one thing that tells us that we're on the right track here by introducing something like that. And I could introduce this as a definition, and I'll call it the transverse metric. This piece over here would be the longitudinal metric, and longitudinal refers to the preferred time direction given by the congruence. Another property that's interesting is that, I won't prove it here, but it's really very trivial. If you multiply H with itself, you get H back. And that's really trivial. You just multiply what H stands for, and you do the work, and you find that this holds. Another thing that you can verify is that the trace of H is equal to 3. Because the trace of H is going to be equal to the trace of the metric, which is 4, plus the trace of this guy, which is U alpha, which is -1, so you get 3. So what do we have here? Well, H is really a projection operator. And it's a projection operator that takes you, away from the direction of U into the orthogonal directions, which I'm defining here to be the spatial direction. So the direction of U is going to be the time direction for us. Everything orthogonal to U is a spatial direction. H is orthogonal to U. H has this property that projection operators have. And therefore, you can think of H as something that projects down to the purely orthogonal part of the space-time orthogonal to U. So it's really a projection operator. But let me go back to this, because that was really the starting point. And let's make sure that this is something we all see very clearly. Why does it come from? So let's imagine that we're selecting a point here somewhere in a congruence. Let's say this point over here. And I'm going to be introducing here a local Lorentz frame at that point. And I'm going to align the time direction of that Lorentz frame to be aligned with the direction of the vector field at that point. So in a local Lorentz frame, momentarily co-moving with the reference geodesic, we know that in that special frame, the velocity vector is going to be pointing purely in the time direction in that frame. That's what I've been saying all along. We also know that in that coordinate system, the metric is -1, +1, and a bunch of zeros. If I want to invent a notion of a spatial metric in that frame, I know that what I need to do is to preserve those +1s, but take out this -1. So the h alpha beta I would like to have in that frame would be one where I kill off the entry up here, but I keep all the other ones. That would be what I would mean by a spatial metric in that frame. And now the remaining question is, well, how do I define this tensorially from this and that? And it's pretty clear that if I need to kill off this entry, what I need to use is this one over here. Right? So if I want this, and I have that, then it's pretty clear that what I need is this definition, because this multiplying by that will give me a +1 that will kill off this -1 and will produce the 0 that I wanted over here. So the bottom line is that, well, this is something I could, guess by just working locally like this in the local Lorentz frame. I play around with this, that's what I want, and I declare that this is going to be the proper tensorial definition. I first get it by playing around in the Loken frame, but this is a tensorial equation involving a whole bunch of tensors, so it's fine. It's valid in any coordinate system, in any frame, and that's basically the motivation for doing this here or doing this here. You had a question? No. No? Okay. So that's a very important thing that we're going to be needing. It's going to be, a description. It's a notion, basically, of a metric tensor that applies only in the spatial directions. And what I mean by that is the directions that are everywhere transverse, everywhere orthogonal to the direction of the time-like vector field. So that's why I called it the transverse metric, and that's something that really describes the spatial structure around the congruence, or within the congruence. And this will be very important for what we're going to be talking about next. Okay. Okay, so having introduced this, I'm going to come back to that equation over here. If you look at this, you'll recognize that from what we talked about before. So the behavior of a neighboring geodesic relative to the reference geodesic is captured by that equation, which states that the rate of change of the deviation vector as I follow the congruence in time is going to be given by the gradient of the velocity field times the displacement vector. Rings a bell? So I'll call it d alpha beta c beta, and b alpha beta is the gradient velocity field. So we've seen that in the fluid case. In the fluid case, this was the result of a Taylor expansion truncated to leading order. Here, there are no approximations. It's an exact treatment. By the way, this comes out as an exact equation precisely because we've made sure to define the deviation vector as tangent to cross curves. You can find treatments of this in older literature where the displacement vector is defined in a sort of pedestrian way as a difference between coordinates here and coordinates there. And if you do that, well, you run into trouble, first of all, conceptually in terms of differential geometry, but you also introduce an essential approximation that tells you that this is only valid at first order. But if you do it properly the way we've done it in terms of tangent vectors to cross curves and all of this, this turns out to be completely exact with no approximation. But this is an equation we can recognize. It's basically the congruence equivalent to the equation that was our starting point in the fluid case. This is the rate of this is the rate of evolution of the deviation vector, which is linear in the deviation vector times the gradient velocity field. Right? So that's a nice equation. Lots of content in that equation, and what I want to do now is to bring it out. In the fluid stuff that we did, nothing had time components to them, right? Our vectors were purely spatial. Here we have some notion of that too, because my deviation vector is also purely spatial. It has no time component. Well, let's see what else we have. So we have B. So let's work out whether B has any time components to it. And the claim is that there are no time components. So we can prove very quickly that B alpha beta is 0 if you multiply it by U beta. So its time component in the second index is going to be 0. And its time component in the first index is also going to be 0. So B is a purely spatial tensor. Or purely transverse, if I keep my terminology straight. Other than that, of course, B is going to be some matrix, some tensor that has no particular properties, no particular symmetries. And the same decomposition that we used before for B in the fluid case, we're going to do it also here for the congruence case. But that I'll do in just a second. First, I want to prove this right here. Well, the first one is obvious. B alpha beta U beta is just U alpha comma beta, semicolon beta, U beta. And that's 0 by virtue of the Judy's equation. So if I was dealing with a congruence of time-like curves that are not geodesics, that statement would not be true, and we would have to work a little harder. But this statement now is automatically true. For the other guy, we get U alpha semicolon beta, and we've done something like this before. I claim that this is the same thing as U alpha differentiated with respect to beta. And that's 0 because the velocity field is normalized to -1 everywhere. So both properties are true, and therefore B alpha beta is a purely spatial tensor. Well, the B matrix that we were dealing before in the fluid case was also purely spatial. So the decomposition of B into irreducible pieces that we used before can be used here too. It's going to be the same thing. It's going to involve exactly the same ingredients because we're really dealing with the same kind of object. I mean, we write it in terms of space-time tensors, space-time indices. So formally, it has additional pieces to it. But those pieces are trivial. They're zero by virtue of that. So in a local Lorentz frame of that kind over here, that guy will always have zero entries along time and will be purely spatial in that frame. And therefore, in that frame, there, the decomposition will be exactly the same that we introduced before. So I'm going to introduce exactly the same decomposition of B in terms of irreducible pieces. Everything will have space-time indices because we are working in space-time. But the very important point here is that, well, in fact, the time entries are trivial. And really, we are dealing here with purely spatial tensors. So anything that I said in the fluid case that was purely spatial in nature applies directly because this is also purely spatial in nature. So the decomposition will be the same. The interpretation of all the terms is going to be exactly the same. So that's why I took the time to do it for the fluid case because I don't want to do it again here. The interpretation is really exactly the same. You have a question?
Yeah, so they're only trivially zero if it's a finely parameterized, right?
Yeah.
So if it's not, we
If
don't
you-
lose all the other.
Right. So if I didn't do that, if I chose an arbitrary parameterization, then one of those guys would not be zero. Instead of that, we would have something involving kappa and involving the velocity field again. There are ways to deal with that. I mean, you can work around that, but it introduces complications that are really not essential. Although I should point out that at some point we're going to be doing this for the null case. For the null case, it turns out to be very useful for many applications to have a non-affine parameterization, and for those cases we'll have to we'll have to come back to that issue when we deal with the null case. We could deal with this issue right here, but I didn't think it was important to do it here. But yeah, it's a good point. Okay, let me just do that, and then we'll quit. And before we quit, I'll give you the homework assignment before I forget. So, decomposition of B. So B alpha beta, again, is something that by itself doesn't have any symmetries. So we break it down into a bunch of things that do have a lot of symmetries. The first guy is going to be the trace term. But notice that I'm not defining this in terms of the full metric. I'm using the spatial metric instead, the transverse metric, because I know that this is something that should not have time components to it, and I'm going to build it up from things that don't have time components to them. So I'm using the spatial metric here. I'm defining a shear tensor, and I'm defining a rotation tensor. And again, these things have, Lorentz indices to them. We're talking about space-time tensors. But we are talking, in all cases, about space-time tensors that have no zero entries if you work in a local co-moving frame. So all of those tensors are going to be orthogonal to U. So that means this one, this one, this one, and that one. That's going to be the expansion parameter, the expansion scalar. This is going to be the shear tensor, and this is going to be the rotation tensor. And because this is essentially the same equation we encountered in the fluid case, and because this is essentially the same decomposition that we encountered in the fluid case, the interpretation for all of these things is exactly the same. So theta is defined to be the trace of B alpha beta, and you can verify that this is there's no contradiction between this and that, because if I multiply this equation here by h alpha beta, I get h alpha beta multiplied by h alpha beta, and from the equation I have over there, that's the trace of h alpha beta, which is 3. So you kill off the 1/3, and you pick up nothing here, and you pick up nothing there, because this has no trace part. This is antisymmetric. So that's the definition of theta. But in fact, we could write it also in terms of the full metric, because the difference would be a term in UU, and that would kill the B, because B is orthogonal to U. Right? So this is really the proper definition, but we can write it in this form. And if we write it in this form, what this means is that we're talking about the covariant divergence of the velocity field. Sigma is defined to be, well, the symmetric part of B alpha beta minus its trace piece. That's an H. And omega is defined to be the antisymmetric part of B. And when you put it all back together, with those definitions, well, you get this equation back. And I could write it right now. So all of these things have the same interpretation as in the fluid case. And one example is that the expansion parameter is now going to be given by the proper time derivative of volume elements. So the picture here is that, as you follow trajectories, you take the transverse view and you have basically volume elements. So you have your reference word line over here. You have a bunch of word lines around it, so you can define a cross-sectional volume that is anchored by the geodesics. And as you follow the behavior of all those geodesics, you find that those cross-sectional volumes change. I mean, the shape, of course, the shape of those cross-sectional volumes will change. That's going to be governed by the shear tensor. They're going to rotate or twist. That's going to be governed by the rotation tensor. But the overall scaling or shrinking, expansion or shrinkage of the of those cross-sectional volumes will be governed by the expansion parameter. And following basically the line of reasoning that we followed in the fluid case, we can show, and I have other ways of showing this in the book, that theta is really the fractional rate of change of those cross-sectional volumes as you follow the behavior of neighboring fluid elements or neighboring geodesics around that reference geodesic. So same mathematics, same spatial properties, and basically same interpretation. Okay, so I'll quit now, but I just want to give you your first homework assignment before I forget. And then we'll reconvene this afternoon. So a few problems from chapter 1, so section 113. I want you to do problem number 3, problem number 6, and problem number 9. And in section 2.5, I'll give you more problems in the second homework, but right now I want you to work through number 1 and number 3. And I'm giving you 2 weeks to do that, so I want them back by February 8th. So that's 2 weeks from now. And February 8th is also the time where I need you to have submitted your proposal for a term project. So far I've received one proposal, so all of you are registered in the course have to get back to me for approval before February 8th. And as I told you before, what I need is a paragraph from you, explaining what you intend to do, what sources you intend to work from, and all of that. So it's not too late, but that deadline is approaching, so please give it some thought. Okay, any questions before we quit for lunch? Okay, so I'll see you back here at 3:30.